All right, so this tutorial is going to be slightly different style than the previous ones. You know, the previous tutorial sort of went through lots of results in their respective fields. You know, people are really just beginning to think about the relationship between privacy and game theory, and in fact, we're going to have a session on it right after this, so I don't want to sort of give away those results that are known. So instead, you know, sort of what I want to do here is first give a brief tutorial just on game theory so that everyone understands the basics of the sorts of problems that we're going to be hearing about next, and sort of give motivation for why people who are interested in game theory, maybe they should think about privacy, and vice versa. Why people who care about privacy, maybe it's worth thinking about game theory. Okay, and sort of for this reason, questions are absolutely welcome. Please interrupt me if anything I say is not clear. I also don't need to get through all of the slides. It's much better if everyone understands sort of the beginning slides. So let's just sort of take a wide view first and think about, you know, those of us who are computer scientists at least, you know, we're used to thinking about designing algorithms. So let's think about what's the difference between an algorithm and a game. Okay? So if we have the luxury of controlling the whole system, you know, all of the moving parts, then we can just design an algorithm. We can specify what every part of the system does, and we design it so that it does what we want. Okay? On the other hand, occasionally we are in the position where, you know, there are these sort of annoying agents that are part of the system that we don't have full control over. Maybe these are somehow, you know, self-interested agents in some way. You know, some participants with agency, you can think about, you know, this happens naturally if what you're designing is a network, but the canonical examples are things like auctions. Right? So sometimes you do not control the whole system, and therefore, you know, the best you can hope to do is sort of design the constraints and incentives to try to, you know, essentially trick the agents who can do whatever they want into doing what you want. Okay. So, you know, there's sort of people talk about game theory and mechanism design. You know, you could sort of think about them as sort of inverses of each other. So, you know, typically when someone says game theory, what they mean is, well, maybe there's some fixed interaction. We sort of understand what are the rules of the game, rock, paper, scissors. And what we want to do is model what are the incentives of the players who are playing it, and ideally use our model to predict their behavior. We want to predict what's going to happen. Okay. On the other hand, you can sort of think about mechanism design as reverse game theory. Maybe there's not some fixed interaction. Instead, you know, we've got these rational self-interested agents, but what we get to do is design the rules of the game. And, you know, since we have some model from game theory about how they'll behave, we want to design the rules to shape their behavior. So I want to sort of begin by saying that there's a strong moral connection between mechanism design and private algorithm design. Okay. In both cases, you know, what we are doing is designing an algorithm to act on data when the data does not belong to us as the designers of the algorithm. In the mechanism design case, the data belongs to the participants. Maybe it's their sort of reported types. And well, in the private algorithm design case, you know, again, maybe we are lucky to act as curators of the data, but it's not exactly our data. We identify each piece of data with some person. Okay. And we sort of have to manage their incentives. Right? In the mechanism design setting, the individuals are experiencing some utility as a function of the outcome chosen by the mechanism. On the other hand, in the private algorithm design setting, again, we're designing mechanisms that take as input the data and choose some outcome. And we're imagining that the individuals are experiencing some cost as a function of, you know, either the outcome directly or consequences of that outcome. Maybe they're going to be denied health insurance. Right? And the point of differential privacy is somehow to manage those incentives. We want to mitigate those costs. Similarly, in mechanism design, we want to manage the incentives of the individuals. And in mechanism design, explicitly, we have to incentivize individuals to participate. That's sort of one of the axioms. If we don't incentivize individuals to participate, they won't. And what I want to suggest is that this may also be true in private algorithm design. And I think this is one of the best ways to motivate the definition of differential privacy. It's sort of a utility theoretic way of promising individuals that nothing too bad will happen to them if they participate. Okay, it's just, the first step of a data analysis task is collecting the data. So we really have to incentivize people to participate here as well. Okay, so why should we care about game theory, right? And why should we care about privacy? Maybe you care only about one of these things. So what I want to suggest is that, well, maybe there are sort of three goals, at least, that we might shoot for. Okay, so the first is that at this point, differential privacy has given us a collection of definitions and tools for thinking about managing risk, managing uncertainty, talking about noise, and potentially tools from differential privacy can be brought to bear to solve problems in game theory that we would like to solve. And there's already been a lot of work in this direction, and we'll see some of it in the next session. Now, I think also that ideas from differential privacy can also be brought to bear to model costs for privacy in mechanism design. I think this is something that the economics literature has up until now largely ignored, which is that a standard assumption is that people's utilities are a function only of the outcome of the mechanism, but sort of what we learned from differential privacy is that it might be useful to think about your costs actually as being a function of maybe the process by which the outcome is computed. And there are plenty of cases in the real world where you're in some game theoretic setting and it's extremely plausible that people care about privacy. And if we want to think about how to incentivize people who care about privacy to do certain things, we need to model their costs for privacy. And maybe differential privacy has something to say here as well. And there's a lot of work on this question as well. We'll see some of this in the next session. And then something that hasn't been explored quite as much, but I think there's room for this as well. Are there tools from game theory? Is there ways in which game theoretic thinking can be brought to bear to solve problems in privacy? There's been less work on this, but I think that it's a very interesting question. And just some suggestions. One of the immediate questions that you might like to answer is, well, okay, how are you going to collect the data, right? The first step in any data analysis task is collecting the data. You want to figure out a way to collect sort of maybe an unbiased sample of some population in a way in which you're compensating people for their costs so that they are happy to participate. There's been some work on this. And an interesting question is maybe to sort of, since I've been talking to economists, endogenize epsilon. Right? If private data analysis is useful, it's worth money to someone. On the other hand, the people who own the data, they experience some cost as a function of the use of their data. So, we should be able to sort of solve for epsilon, sort of as a market clearing price. So those are just some high-level ideas about how these two fields might interact. Okay, so now what I want to do, since I assume everyone here is familiar with differential privacy and perhaps not everyone is familiar with game theory, is just give you a crash course in the very basics of game theory. Okay. So first of all, what is a game? So a game is specified by three things. Okay. First, we have a set of players. I'll count them as 1 through n. Next, for each player, they'll have a set of actions. Okay. So for every player, there's a set of actions that they can choose to play. And finally, every player has a utility function. It tells them, for every collection of actions that everyone might play, including themselves, how happy are they with that outcome? Okay, so I'll measure their happiness with a real number, something between 0 and 1. Okay, so every player might have a different utility function. And we're thinking of players as wanting to behave in this game so as to maximize their utility. Okay, so everyone is familiar with games already. Here's rock, paper, scissors, just sort of described in this format. There's two players here, the row player and the column player. Each of them has three actions, rock, paper, and scissors. And what this matrix specifies is their utility for every pair of actions. So if I play rock and my opponent plays paper, well, paper beats rock, so I get utility, say, -1, I lose, and my opponent gets utility 1. Okay? So these three things specify a game. Okay, so once we've specified a game, what does it mean to play a game? Well, the playout of the game sort of can be described by the following objects. Okay? So first of all, I might talk about a strategy for a player. And in particular, I might talk about a mixed strategy, which isn't just a choice of action, but might actually be a distribution over actions. Okay, a mixed strategy, players can employ randomization when playing a game. Okay. And it'll be useful to talk about what strategy everyone has chosen. I'll call such an object a joint strategy profile. It's just a strategy, one for each player. You can write it out as a set of strategies. And some useful notation that comes up, it's convenient in game theory. Sometimes I'm going to want to talk about what's the joint strategy profile of every agent excluding agent I. Okay, and so I'll just denote this S minus I, and it's just the choice of strategy for every player J not equal to I. I have not specified what player I has done. All right, so this is just notation so far. Now here's how a game is played. Okay, these are simultaneous move games, and again, think about rock, paper, scissors. So first of all, simultaneously, every player will pick a strategy, a distribution over actions, and each agent will derive utility as defined by his utility function. And when we're talking about mixed strategies, well, there's randomization involved, so we'll talk about the expected utility. Okay, and the idea we want to get at is that agents are going to behave so as to maximize their utility, whatever that means. Okay, so we want to use sort of this framework to make behavioral predictions. Okay, and so let's try to think about that. Sometimes this might be relatively simple. It might be simple to decide how to play in a game. Okay, so maybe I'll say that an action AI, for some player I, is a dominant strategy if for every choice of actions for the other players, for every choice of actions my opponents might make, independent of what they are, and for every deviation I might consider, instead of playing A, maybe I'll play A prime, I can tell myself, well, playing A is always better than playing A prime, no matter what everyone else does. Okay? And maybe we'll talk about an alpha approximate version of this, in which case playing A might not be better than every action, but I can never gain more than alpha by switching to another action. Okay, so if I have at least an exact dominant strategy, it should be pretty easy for me to figure out how to play. I don't have to think about what my opponents are going to do at all. I just have to play A. No matter what they do, if I played A prime, it would always be a mistake. Yeah.
So what is the expectation over here?
The expectation. So I guess my opponent. So yeah, you're right. I guess what's not quantified is A minus I should still be selected from the set of mixed strategies of my opponents. So if I have a dominant strategy, it's a fixed action, but I should always be doing better even if my opponents are playing mixed strategies. Okay. So if we are lucky and the game is such that every person has a dominant strategy, then it's easy to predict how rational players should behave, at least if they are reasonably smart. Right? If everyone has a dominant strategy, a unique dominant strategy at least, then they should play that action, the dominant strategy. And so when it exists, we can call a joint action profile for all of the players a dominant strategy equilibrium if for every player the action they are playing is a dominant strategy. And again, we can extend this to the idea of an alpha approximate dominant strategy equilibrium. So when this thing exists, it's great. We're not assuming much coordination or computational power. We're not assuming much about our players to say that they'll play dominant strategies when they have them. Okay, on the other hand, dominant strategies do not always exist, unfortunately. In particular, in rock, paper, scissors, rock is not a dominant strategy. It's beaten by paper. And you can go through all three of your actions. None of them are dominant strategies. Okay, so to dominant strategy, equilibria in particular don't always exist. And so it's not a maybe not a sufficient prediction if because just in certain interactions it's not something that exists. So we can talk about when dominant strategy equilibria don't exist, the problem of predicting what people are going to do becomes a lot harder, and maybe the predictions become less plausible. But at the very least, we can attempt to identify stable solutions. If somehow we're allowed to update our strategies for whatever reason, we can identify stable solutions where nobody has any incentive to change. And that's what a Nash equilibrium is. Okay? So we can say that a joint strategy profile, which is, again, just a collection, one strategy for each player, here we're allowing randomization, is a Nash equilibrium if for every player I, and for every deviation A that he might consider, maybe I'll consider switching my action from SI to AI, it should be that I cannot gain anything by doing that given what everyone else is doing. Okay? So no player can unilaterally change his action in a Nash equilibrium and gain anything. Okay? So it's at least a stable solution. And again, we can talk also about alpha approximate versions of this, where we just mean, well, maybe some player can gain by deviating, but not very much at most alpha. All right. Okay. So, sort of a basic, not trivial, but sort of foundational fact is that Nash equilibria always exist in games. This is what John Nash proved. And so the Nash equilibrium of rock, paper, scissors is to uniformly randomize between rock, paper, and scissors. If I do that, then there's no strategy that you have that will sort of beat me more often than I beat you. But there's the caveat that if we want to say these things always exist, then maybe we require people to be able to randomize. Okay, so that's a whirlwind tour of game theory. Now let's talk about mechanism design. Yeah.
I have a question. So I've heard various answers to this question before, but why is it that expected utility is sort of the right thing to consider? That is, if you're risk averse or something, then maybe you don't care about the expectation of the utility. You care the probability that it exceeds some value or it doesn't exceed some value.
That's right.
And and then how does that play with the note? I guess I can think of a few ways around that, but then they screw with the alpha.
Yeah. So certainly, there's this implicit assumption through lots of game theory that agents are what's called risk neutral, which is basically that they only care about their expectation. You can talk about risk-averse agents that maybe have, concave or convex utility functions. And there's ways to talk about that. So the min-max theorem doesn't just hold for these risk-neutral players. In a concave convex game, there's also an equivalent min-max theorem. But it gets it's hard to sort of justify maybe the particular function. So that's absolutely right, and this is a limitation of sort of the model of rationality that is used throughout lots of game theory, which is that we assume that people are risk neutral. And there's work trying to address this, but it's I don't think there's any sort of universally accepted way of handling this. It's a modeling question. But it's an excellent point. Yeah.
Well, can model it as a part of the utility function?
Say that again?
So the utility function can be a function of let's say, as a function of the distribution of the mixed strategy. So here you don't need to take the expectation. The expectation is inside the utility function.
Well, I guess you could define it that way, but I did not. So we have the expectation outside.
I think that's you don't need to worry about whether the agent's risk averse or risk neutral.
Well, you'd still have to worry about this at some point. The question is, what is your utility for some collection of distributions? If you've defined the utility for sort of the corners of this simplex, then you just linearly interpolate to figure out what's the utility for a distribution. You could, and that's sort of like taking the expectation. You could define some other way to do it, but you'd have to specify. And people would complain about the particulars of your specification.
I think in that way, can we just change your utility function?
So that's the standard response, which is that any complaint about the game should be just encoded in the utility function.
Yeah, I think that's where the Nash equilibrium always lives.
Yeah, but it's not. I mean, this is a real issue. It's not just a syntactic thing. That is, when we're talking about utility like this, we really are assuming that you are indifferent between $1 million and a lottery where half the time you get $2 million and half the time you get 0. And if that's not the case, you'd have to define a different utility function. Right. Yeah.
So until now, the game is played only once, right?
Up till now, we're talking about single-shot games. Yeah.
I didn't understand the difference between Nash equilibrium and the dominant strategy.
So a dominant strategy is something that you should be happy playing no matter what everyone else plays. You don't have to think about what they're playing when you're thinking about how you should play. A Nash equilibrium is just a stable solution. It says the thing you're playing is optimal for you given what everyone else is playing, but if they were playing differently, you might want to play differently yourself. Other questions? All right. So, okay, Nash equilibria always exist. So let's talk about mechanism design. Okay, so this is sort of the reverse of game theory. We're going to design the rules of the game and try to shape people's actions to conform to what we'd like them to do. Okay, so I'll put this back into the notation of a game in a moment, but for now, what's a mechanism? Well, everyone's going to, and this should, by the way, be a little familiar to people who are used to thinking about what's a private mechanism. So the input to a mechanism, it's some partitioned vector. There's one report for every agent in the game. Okay, so the input is a vector of n types. Each agent selects a type and reports it to the mechanism. And then the mechanism, in some way, chooses an outcome from some set O. Now, based on the reports. Okay, so let's imagine that agents care about which outcome occurs. So they have some valuation function which maps outcomes to their happiness level, which is, of course, a number between 0 and 1. So the mechanism has potentially the power to charge prices to each agent as well. Okay, so in addition to choosing an outcome, maybe the mechanism can decide to charge you some amount of money. And it's also going to decide how much money to charge you based on what the aggregate reports were from every person. But, and we should keep this in mind, we may or may not be in a setting in which the exchange of money is allowed. So it might be interesting to consider the constrained setting when the prices have to be 0 for every player. Okay. So once you define a mechanism, this defines a game. The set of actions for each player, it's the set of reports that they can make to the mechanism. The utility function for every collection of actions, for every collection of reports, it's the value that the player has for the outcome that the mechanism chooses given those reports, minus the amount of money he has to pay, the amount of money that is charged to him, which is, again, a function of the aggregate reports, one from each player. Okay? So this fits into our definition of what a game is. And this is really sort of a reduction, sort of a foundational, very simple result in the economics literature, which is called the revelation principle. It says that we can, without loss of generality, take this type space to just be the set of allowed valuation functions, rather than having you report some, constrained, funny type. I can just ask you, what is your valuation function? And the proof of this is really just a reduction. If you had some other mechanism, then I could put a black box around that and ask you what's your valuation function, and then in the inner mechanism I would just play whatever action was in your best interest. For example, if we're going for dominant strategy solutions, I would just, given your valuation function, have some other bot play the action that you would have played. It's called the revelation principle. So we can think about these mechanisms as just asking you for your valuation function. Still, depending on how we design the rules of the game, it might not be in your best interest to tell the mechanism the truth. So how should we design what should the mechanism do given the reports? So, if we're algorithm designers, we might say, okay, well, why don't we just design the mechanism to optimize our objective? We have the reports, we'll just optimize, we'll pick the outcome that optimizes whatever our objective is. And the problem is, if we don't incentivize truth-telling, then our data is wrong. We're probably optimizing with respect to the wrong data because people won't tell us their true reports. So we think we're finding the optimal outcome, but we're not because we didn't have the right inputs. So this is why we'll often want to design mechanisms that are dominant strategy truthful. We want to design the rules of the game so that truthful reporting is a dominant strategy. Okay? We'll just say that a mechanism is dominant strategy truthful if for every agent reporting her true valuation is a dominant strategy. And we can again talk about approximate versions of this concept. Okay? So we could also talk about implementation in Nash equilibria, but when we can, it's nicer to talk about implementation in dominant strategies because it allows us to assume less about the rationality of the people playing the game. Okay, so this is a privacy workshop. How can privacy possibly help in this endeavor? So everyone remembers what differential privacy is, but let's just sort of syntactically think about it in terms of mechanism design. So, this mechanism in the mechanism design context, we can think about it as taking as input a database, right? It takes as input a collection of types, one from each agent, a collection of reports. That's the private data. And we all know the definition. The mechanism is epsilon differentially private if for every pair of neighboring databases, so for every pair of vectors of types that differ in just your input, the probability of any event doesn't change by very much. Now, when you are considering whether you should unilaterally deviate, whether you should change your report truthfully or report some other type, the choice that you have is whether we should run this mechanism on the database T or on some other neighboring database T prime, which is the same in every coordinate except for yours. Okay, so the choice you are facing when deciding whether to lie or not to the mechanism is whether the mechanism is going to be run on one of two neighboring databases. So here's an equivalent definition, completely mathematically equivalent definition of differential privacy. I think I first saw Kobi Nissim give this as the definition of differential privacy. I think it's a very nice definition in this context. It's the same definition. You say that a mechanism is epsilon differentially private if for every possible valuation function, right, so for any function you could possibly define, mapping outcomes to numbers between 0 and 1, and for every pair of neighboring databases, if we look at what's the expected value of selecting an outcome from the distribution defined by the mechanism input on distribution on database T, it should be at most e to the epsilon times the expected value of selecting an outcome from the mechanism based on database T prime. Right? So it's really promising that no matter what it is you care about, no matter what your valuation function is, your expected value doesn't change by very much, whether you participate or not, whether you lie or don't lie. Just to see that this is equivalent, well, in the one direction, of course, what's an expectation? It's just the sum over all outcomes of your value for the outcome times the probability of the outcome. So if the probabilities don't change by more than a small factor, then neither does the expectation. In the other direction, this holds for all valuation functions. So we could just define a valuation function, which was the indicator vector for the indicator random variable for the event that you cared about, in which case these expectations are probabilities, and we get the old definition. Okay? So this is sort of a nice way of seeing that what differential privacy really promises is freedom from harm, because whatever it is you care about, you can model it in this valuation function. Okay? So when you write it this way, the following sort of observation of McSherry and Talwar is immediate.
So, Aaron,
yeah.
Can you go to the previous slide? So you said differential privacy guarantees freedom from harm.
Yes.
I think what it guarantees is relative.
Absolutely relative freedom from harm. So It's possible that according to your evaluation function, you will be very unhappy once we run this mechanism, but you would have been almost equally unhappy had you lied to us. So you might be, you might come to great harm, but it's not our fault. Okay. So, right, an immediate observation, this was first due to McSherry and Talwar, is that an epsilon differentially private mechanism is also epsilon approximately dominant strategy truthful. What's the reason? Well, it follows directly from the definition. When you're considering whether you should lie or not, you're considering whether we should run the mechanism on one of two neighboring databases, and it's promising that your expected utility is not going to change by more than a 1 plus epsilon factor. Okay? And we sort of, remember, we defined the utility functions to map to this bounded range 0, 1, so we could think about this like an additive epsilon loss. Yeah.
Does it admit that you also have nothing to lose from lying?
Absolutely. So differential privacy is actually both stronger and weaker than truthfulness. On the one hand, it's weaker since it only guarantees approximate truthfulness. On the other hand, it's a stronger constraint. It's actually saying every strategy is an approximate dominant strategy. So that's an excellent point, and we'll hear more about that later today. Yeah.
It's also not clear that you are not at fault because of the harm, because it could be that because the statistic was such that got used in a way, although the statistic did not depend on your individual data very much, maybe it's about race, and that the race got used to decide insurance rates.
That's right. So you're absolutely right. I, as the mechanism designer, may be completely at fault. For example, if I decided to run a study correlating smoking and lung cancer, if your insurance rates go up as a smoker, it's because I ran the study. So maybe a better description is that you can't do anything about it. So this is a very good definition for someone who wants to run such a study, because once I've decided to run the study, you may as well participate. So this is from a utility, people running studies should really like this definition because it allows us to do things that potentially harm people and still they have no reason not to participate. There are also other, it's an excellent definition and there are other ways to motivate it. Okay, now there's, okay, so it's not exact truthfulness and everything, it actually promises that everything is an approximate dominant strategy. But there are also some advantages that you don't get from sort of the standard solution concepts, which are that it's naturally resilient to collusion. If two people change their action, well, we get a guarantee of 2 epsilon differential privacy. So nobody can, no pair of 2 people can gain more than 2 epsilon by deviating. Okay? So normally a dominant strategy mechanism could completely fall apart in the face of collusion, but not private mechanisms. Notice we're getting this guarantee without any payments. So normally in mechanism design, payments are a very important part. And if you can do this, then it means that maybe you can use the mechanisms in some settings where otherwise you can't. Mechanism design is also sort of very hard. It's only well understood in very simple single parameter settings. On the other hand, we have generic sort of private mechanisms. You can apply the exponential mechanism even in very complicated settings and still get these strong, although approximate, guarantees. And not least of all, it's privacy preserving. So if you're in a setting in which privacy actually matters, where people care about privacy, then running a private algorithm is an excellent thing to do. Okay, so what are the research questions? So it's already been brought up that differential privacy is not, does not imply exact truthfulness. And maybe this notion of approximate truthfulness, it's not as strong as we would like, because in the end, remember, we want to make predictions. And if everyone's playing, everything is an approximate dominant strategy, why should we say that you're going to play truthfully? Well, you could tell stories that maybe, there's some mental effort in coming up with a good lie. Maybe the easiest thing to do is tell the truth, and since there's so little to gain in lying, you might as well. But this is a completely valid criticism, and you might ask for exactly truthful mechanisms. So maybe differential privacy can still be used as a tool in designing exactly truthful mechanisms. And we could ask for mechanisms with payments or without. And maybe we could sort of do this while still maintaining the nice collusion and privacy properties that we get from sort of differential privacy as a solution concept. Okay, so the answer to this question is yes. I'm not going to talk much about it, but there are plenty of people at this workshop that you can talk to. A paper just at this last Fox by Ji Huang, who is here, showed that if you add payments to the exponential mechanism, you can actually make it exactly truthful, and you can add noise to those payments, and so the payments are private as well. So you can get an exactly truthful mechanism that still has the nice properties that come with privacy. Yeah.
I have a question regarding the dominance of this strategy. So you define dominant strategy as a strategy no matter in which you choose an action, and no matter what is the other actions of the other players, you still win.
Mm-hmm.
But here, actually, what happens if half of the players or half of the database entries were changed, or half of the players lied? In this case, you will not guaranteed to achieve the privacy guarantee here.
So what you're saying is true, but it does not fit into that's not the right comparison to dominant strategies. So remember, what was the definition of a dominant strategy? No matter what everyone else does, it's not in your best interest to change your action. And the approximate version was you cannot gain very much by changing your action, no matter what everyone else does. It does not speak to what might happen if 10 of us change our action. So what this is saying, if a mechanism is private, then no matter what everyone else does, we don't have to assume they're playing anything in particular. If you consider whether you should change your action or not, the gain you can get is never more than epsilon. So another question maybe is, can differential privacy help us build mechanisms under weaker assumptions? Okay. What if we're in a setting, as we frequently are, in which the mechanism designer does not actually have the power to compel outcomes? Maybe instead of forcing you to do some number of actions, the only thing he can do is suggest an action. Right? Another way of sort of stating this is, what if participating in your mechanism is optional? What if agents have the option to play the game independently of the mechanism? Again, the only thing you can do is make suggestions, and you want to incentivize people somehow to follow your suggestions. Okay? So this is granting weaker powers to the mechanism, which means maybe we can apply such mechanisms in broader settings. If we want to do this, can privacy help? The answer is also yes. We'll hear about it next session. Another question you might be asking is, well, why are we designing mechanisms which preserve privacy? I mean, why would we do this as mechanism designers? Well, presumably it's because agents actually care about the privacy of their type for some reason, right? It could be that, we're figuring out where to put a hospital, and your type is a function of, your medical data. Do you have a disease that's treated at this hospital, right? So privacy might be important for the same reason it's important in all of these other settings. Privacy might also be important for purely game theoretic reasons. Maybe there's some unmodeled future interaction in which if other players can learn about my type, they can exploit me. Maybe we're bidding in some kind of auction that's going to be repeated. We're going to buy fish today, but we're also going to buy fish tomorrow and the next day. And if people learn exactly my value, maybe they can take advantage of me. So maybe just for strategic reasons tomorrow, I care about the privacy of my type today.
Arguably, those are the same.
Arguably, they're the same. I think mathematically they're the same, essentially. I just want to sort of emphasize that there's the sort of reasons why data might be sensitive that we normally think about, and then there's reasons that are it's not intrinsically that how much I can sell fish for is like deeply private to me, but because of game theoretic reasons it is. But they're the same. Okay. But so far this is sort of unmodeled, right? I mean, we said people have utility functions that are defined as values over the outcome, okay, minus payments. But we're not explicitly modeling anyone as actually caring about privacy, right? So this is sort of a funny thing. On the one hand, we're saying maybe we would like to have mechanisms that preserve privacy because people care about privacy. On the other hand, we haven't modeled how people care about privacy. So this is something presumably we'd want to rectify, because once we, once we change people's utility functions to care about privacy, these mechanisms that we designed ignoring that might not be truthful anymore. So an important question is how we should model this. How do you model people's preferences for privacy? And here, differential privacy provides some tools. Remember, immediately from the definition, it's providing, at the very least, a worst-case sort of upper bound on how much harm you can come to as a result of the computation that's being performed. Okay. But it is a worst-case notion, so it's possible that it's sort of too strong in general as a model for what's your cost for privacy. It's an upper bound on your cost for privacy, but it's not necessarily exactly your cost for privacy. So sort of an ongoing modeling question is how should we think about this? If we want to design games, what's the right way to think about costs for privacy? And there's sort of a nice line of work initiated by David Zhao. He's going to talk about it in the next session. Other good people to talk to are Kobe and Salil and Katrina. I don't know if other people on this list are in the audience. You can talk to me as well. But I do want to say that this is still, it's not a settled area. It's an open area that I think is in need of clever modeling. And good evidence of that is I don't think any of these papers have used the same model for cost of privacy. I think there's one paper for each model. So there's good modeling work to be done. Okay, so another question is, okay, well, is this really, suppose we're going to start modeling people's costs for privacy. Is this, maybe we'll just fold this into the utility function and that'll be it. Then we'll just open up our game theory textbook to page 1 and we'll solve all the problems. We just had to model it in the utility function. And my claim is that that's not true. That once we start talking about costs for privacy, that sort of these old standard results in mechanism design may no longer hold. We're in a different ballgame. And the reason, essentially, is because traditionally, people's utilities are thought of as functions only of the outcome, so deterministic functions of the outcome that is realized. Whereas in this community, we've been thinking about, well, privacy is not actually a function of the data that you output. It's a function of the process that constructed it. And that's not something that's modeled in sort of the standard utility model. Okay. Sort of one of the things that doesn't necessarily hold anymore is this, the revelation principle, right? What I said was that, by this simple reduction, we don't have to design complicated games to get people to do what we want. We can just ask them, what is it exactly that you want? What is your type? What's your private data? And then, if we had some other complicated game, we would just play in it for them using their private data. But, that's not very compatible with privacy. I mean, the revelation principle is literally asking for your private data, and this is sort of a direct revelation mechanism, as these things are called, can be sort of maximally disclosive. There's nothing I'm protecting, at least from the mechanism designer's point of view. So a simple example of this is the usually unmodeled first step in any data analysis task, which is the process of collecting the data. If you want to run a study, first you need the data, and in some way or another, you have to convince people to give it to you. Okay? So, yeah.
There's a question on that. To what extent is the issue here the trust in the curator? I mean, if I also trusted the curator to take into account my preferences for privacy, and I had some way of knowing and specifying them, then would the revelation principle still would come back and be okay?
So not necessarily. And so the example I'm going to give, I'm not going to show the details, sort of is in auctions. And the problem, like in an auction, what's your type? It's your value for the good. So I could just ask you how much, is privacy worth to you? And the problem really is that how much privacy is worth to you is probably a function of your private data. So you don't want people to find that out either. On the other hand, how much money I have to pay you is, and how much money the data analyst eventually has to pay, that's always got to be, if I'm going to sort of use your data, it's got to be bigger than than the cost that you will experience, otherwise you won't participate. And the fact that you cannot reveal the cost, and yet the analyst eventually has to pay you that much amount of money, in the end creates a tension.
So I mean, like, even if you trust a curator also to exclude you according to your privacy preferences.
But the fact that he excludes you might reveal something. Like, you're asking for the privacy preferences, and if he excludes you, maybe it's because you value privacy a lot, and maybe that's suspicious. So these are the kinds of difficulties you get into, at least. Okay, so let's maybe give this example by cartoon. So here's sort of the basic data analysis problem. Okay, these are patients in a hospital. The hospital has all their data, and here we are as researchers. And what we would like to do is get sort of maybe aggregate information about this data and run our study. Okay, and the problem is there are regulatory obstacles in our way that might stop this from happening. And this is funny because, again, if we're thinking about these players as economic agents, then presumably it's not that they're unwilling to have their data be used at any price. I mean, everyone has their price. Like, if I offered each of them $1 million if I could use their data in my study, and I'd even promise some differential privacy guarantees, presumably most of them would accept. And, well, the reason we're doing this study is because the answer will be valuable. So someone should be willing to pay. If the study's being run by a commercial interest, there's money behind it. Otherwise, maybe it's funded by a grant. We should be willing to pay for valuable information, and people should be willing to give their data in exchange for payment, at least at some level. So a better solution would be this. Everyone gives their data to the hospital because there are patients there. The researcher gives his grant money to the hospital, who knows the privacy preferences of the agents, distributes the money. Everyone now is happy to share their data, and the study is run. This is something, a market for private data. We might like to build one of these. So let's think about what kinds of concerns we might have. So we could say, okay, well, I've got a very limited budget. I can't pay very much, so I'll just buy data from who I can. So I'll say, who wants $1 for their STD status? Okay, and maybe there are some takers. And I'll run my study, and I will see that in the population of this room, nobody has any sexually transmitted diseases. And the reason is because I got response bias. I offered a very low price, and the only people who participated were those who had low value for privacy, and those were presumably the ones whose private data was not embarrassing. So I did get to run my study, and I didn't have to pay very much, but I got the wrong answer because of response bias. So what's the right price? Well, the typical answer would be to run an auction. An auction discovers the right price, and maybe we can just design a truthful direct revelation mechanism, which is the standard sort of thing to do. So let's do that. I say, okay, how much does everyone want in exchange for their STD status? And people can tell me. This guy wants $1.50. This guy wants 62 cents. That's why he was willing to take the $1 offer. This guy wants $1.25. And this guy wants a lot. And the problem is that's disclosive. Your value for privacy is highly correlated with your private data, potentially. At least if you assume it's not, then you might as well just have bought from the cheapest people if costs for privacy were independent of the data, right? And probably we believe that it is, which means that at the very sort of first step of running an auction, maybe we run into some trouble. right? And this is the problem, that values for privacy are themselves correlated with private data. And indeed, you can show that in this setting, no truthful direct revelation mechanism can guarantee non-trivial accuracy and finite payments. This is a result I have with Arpita Ghosh. Okay. Now, there are ways around this. So Lisa Fleischer and her student Liu, and sort of another way around it in joint work with Katrina Liggett, what you can do is you can do two things. You do have to slightly tweak the way in which you model people as caring about privacy. We have to maybe model privacy costs a little bit differently. And also abandon direct revelation mechanisms. If you do both of these things, then you can get around this impossibility result and design mechanisms which are going to cheaply procure sort of minimally biased samples of data that will actually give you the right answer when you run a private analysis on it. Okay. So that's sort of this is one of the lines of work. There's more papers than this on this question. I don't think we're going to hear about it later in the workshop, but if you're curious, you can talk to Katrina or I. Okay, so another question that isn't really hasn't really been answered in this literature yet, but I think this is one of the promising interactions between, you might hope for sort of a some kind of economic answer to the question, what is epsilon, as part of an interaction between privacy and game theory. Because, in the setting we're imagining, the private data is valuable. It's valuable to the analysts. And it belongs to someone else. It belongs to these participants. And each of them has a different cost for privacy, maybe. But as we've seen, there are some ways for designing mechanisms that can sort of cheaply buy unbiased data. And all right, so this is different than a standard auction for, like apples or something, right? Normally you would buy the goods from the cheapest sellers. Here you can't do that. You need an unbiased sample, so you need to do something more. But you can imagine that there should sort of be a market clearing price for epsilon. What should epsilon be? Well, it's as small as you can afford, or as big as you can afford if you're the data analyst. Okay. So what we want is a market in which people can trade dollars for epsilon, but on Google Images, this was the closest I could find.
A little bit of Photoshop work would have fixed that.
They anticipated the debt crisis when they chose their unit of their symbol. Yeah.
Is it possible to imagine definitions where different people can carry different epsilons in their...
You can absolutely talk about non-uniform, right? So you can certainly have a mechanism in which different people have different privacy parameters in the same mechanism. You might have privacy loss epsilon I might have privacy loss epsilon j, and you can imagine doing something like that and charging us different prices or paying us different amounts of money. There's of course a limit to how much you can do this if you still want an unbiased sample. You can't sort of be too independent of too many people's data if you want accurate answers. But that's certainly a tool that you can attempt to use when designing such markets. Okay, so I'm going to finish up a little early even, I think. I just want to summarize the talk and the messages I want you to go home with. So at a high moral level, I think privacy and game theory both deal with the exact same problem, right? How to compute on other people's data while managing the utilities of those agents in some way. And the claim that is not on shaky ground, because there are some solid results, we'll see some of them in the next session, is that we have built a useful collection of tools for thinking about risk and uncertainty. And tools from privacy can be used in mechanism design to manage sensitivity and noise and to sort of come up with new results that are useful purely from a mechanism design perspective, even if you did not care about privacy. We'll see some of this in the next session. tools from privacy may also be useful for modeling privacy costs in mechanism design. I mean, that's what we're doing, modeling privacy costs. Differential privacy provides a worst case bound, but maybe it's still useful when we're trying to think about how agents are going to reason about their privacy loss. When we change the model to take these costs into account, it's not going to be just redesigning the utility function. It might involve sort of rethinking major parts of mechanism design. Sort of private mechanism design might look very different from non-private mechanism design. And this is something that we haven't seen as much, but I think is worth exploring. Can ideas from game theory be useful in privacy? I mean, we're sort of studying similar problems. There's a field of rational cryptography. Might we see anything that's like rational privacy, where we don't assume worst-case collusions among sort of different data analysts, say, but instead model them not as adversarial, but as rational. If we model their utility functions, maybe we can argue that they won't do certain things, and maybe this will allow us to do more. Okay. So that's my talk, and there's even time for questions.
Let's have a few questions, unless we get back on schedule.
And so there's a lot of criticism about the game theory, about the applicability of game theory to the way people actually act. Now, when we're introducing it into privacy, let's look at the game theoretic model of privacy. Isn't all this criticism even more irrelevant?
Absolutely. So I think that those criticisms are completely valid for every paper that's been written on this topic, and that's, in fact, many of the criticisms for the model considered in paper I can be found in paper I+1. So we haven't figured it out yet. So this is still an open question at the level of modeling. We don't have a technical question. The question is, can we figure out any way to reasonably think about how people think about privacy? And I think sort of obviously, right, any too specific thing we pin down is open to criticism. So what we want is sort of general axioms about how people care about privacy that you might think are reasonable and lead to lots of flexibility. So for example, maybe we can agree that at least differential privacy should upper bound the differential privacy parameter should upper bound your sort of cost for privacy, because we can promise you that your expected utility is not going to degrade, even in the worst case, by more than something that depends on this parameter. And if that's not enough, maybe we can think of some other ones. But for example, by analogy, maybe you don't believe that people are going to converge to a Nash equilibrium in a game, because those are hard to find and there's lots of other problems with them. But sometimes you can define like a broader class of behaviors, correlated equilibria, coarse correlated equilibria, no regret play, that are just becoming strictly more plausible. That is, each described behavior is a superset of the last. So more and more people should be convinced as you enlarge this set. And what we've found is that you can still prove theorems sometimes even in the largest of these sets. So it would be interesting to think about what are the weakest assumptions we can make about people's costs for privacy that still allow us to say something interesting about what their behavior might be. Does that answer the question? Okay.
This is related to the question I asked before, and I just want to see if I understood it right, the kind of comment you made on the correlation mechanism. So if I even know that you're running a study, you put out an ad recruiting for subjects, and I even know that Kobe has seen the ad. I just see him pass by it and look at it on the wall.
Yes.
And then I look at the outcome. There's a risk, and in the worst case, I guess, necessarily will happen that I can compromise. Kobe's privacy might be compromised by looking at the outcome, because he's made the decision about whether to actually follow up based on his.
That's absolutely right.
Privacy.
That's certainly true, and you can think about that as sort of a bug or a feature. So In the work I alluded to with Katrina, we use this as a feature. That is, maybe what we care about is getting the study done, not your privacy. And if I can observe non-participation, if I can ask you a question and observe you to walk away and not answer it, then I learned something about you that harms your privacy, but maybe I can use that in my study. but
or
that
maybe I could make the argument to you, a sort of an offer you can't refuse. Now that you're talking to me, you may as well keep talking, because if you turn around and walk away,
exactly.
everybody's going to know.
By the way, you can do the reverse as well. So in the Lisa Fleischer's paper, she comes over to you and she whispers something in your ear, and the offer is a slightly more complicated contract that is offering to pay you a different amount of money depending on what your type is, if you have an STD or not. And if we know a prior distribution on people's values, for each of these types, I can make you an offer such that your probability of accepting is the same no matter what your type is. So this gets rid of some of the concern of observing whether you accept the offer or not. It requires a very strong assumption. And an interesting question is removing. I have to know a prior distribution on your values.
And there's also another, this gets back to the linearity business, is that, price, all these models effectively assume that, $2 are really worth twice as much as $1 to me.
Yes.
Right, which generally they're not.
That's right. So I'm assuming, there's also this standard assumption about how utility relates to money, and that they're comparable in some linear way. And absolutely right, that may not be true. And again, this is sort of, can be dealt with in game theory, but not, generally is not. There's no, the standard model doesn't deal with this, and you have to make, if you want to deal with it, you have to make decisions about exactly how these things are related, and so there is work on agents who are not risk neutral. This is related to that, or who have decreasing utilities, but it's not sort of the canon. Other question? Yeah.
Any of these considerations have been addressed by prospect theory?
By
Prospect theory?
So I'm not familiar with that term. What is prospect theory?
So it's a model for behavioral economics that takes into account things like framing effects and sort of a different kind of curve where people are more loss averse. It falls off more sharply there.
So you can certainly define any curve you want and sort of study people's behavior under that specific utility function. And there's lots of papers that do this.